Okay, so I think, yeah, most of the parts are well explained except two parts. The first one is the RELU, and the second one that I want to talk is the Softmax. So RELU is just this function. It says rectified linear units, but this is just a max of something. So for example, in a dense layer, we said that there is a expression like plus B, and H was called the weight, and B was called the bias. But when we add the RELU here, the RELU is actually means max of Wx plus B, comma, 0. So this is the meaning of the RELU function. So you can take the linear parts and then you can have the zero parts. And just take the positive of linear parts or 0. And if you have another node here, and it is also the same, that the second node is max of the linear part and then 0. And you have lots of these nodes to approximate some functions which is unknown to us. So that's the point that I wanted to show you here. In this graph, so let's watch the graph again. Okay, I start here. So for example, this is the function that we wanted to approximate. Of course, we don't know this one, but here, right-hand side, there is a max of something, comma, 0. So that is the RELU function operated on some node. And inside the node, we have a linear expression. So in this case, the weight is -3 and the bias is -1. And that linear part is just some line here, and then comma 0. So it looks like this curve. So you can see this curve is actually very similar to the option pricing, the option payoffs. But as we change our -3 and -1 here, we can have many different shapes of the linear lines. So let's keep watching. Now we change the slope. So some parts are not shown in the graph. Especially when weight is 0. So here is another part. So with varying bias, and then if we change the slope, then we can have another lines. So all these are possible lines with just one node. And since we have a lot of nodes, even if the original function is a quadratic function, we can actually use lots of linear functions to approximate the whole quadratic function. That is the basic idea of the RELU function. And I'm going to talk about the Softmax. So I wrote down some stories about me, about the Softmax. So when I first learned this function, its name is not the Softmax. Its name was a logistic function. And that's what I learned in this function when I was 20. And then sometime later, I realized that not everybody call this function as the logistic function. Some people call it a sigmoid function. And I tried to find the reason why they call it a sigmoid function. And the reason was really simple. It looks like a S shape. So they call it a sigmoid function. And then now recently, the many people started call this function as a softmax function. And the people now lots of students have forgotten its original name. Actually, its original name is a logistic function, and the softmax function is a generalization of these logistic functions. But the softmax function, the name, the terminology is so widely used in the machine learning. The people try to, the students in young ages try to think that it was the softmax function, but the original name is logistic. And the reason I learned this function is that the professor that taught me this function, he said that it is a transformation function from -infinity to infinity into a probability. So as you can see, the x-axis can take any value from negative infinity to positive infinity. But this function here, okay, it is disappear, but as it will appear again here. And this function transform the x value into a range from 0 to 1. So this is the illustration of this one. So x is changing, but y is always less than 1. F of x is always less than 1 and greater than 0. Even if the value is very small, the fx is still greater than 0. And then as x goes up, at first it slows up really small, but it goes up really rapidly. And then, yeah, of course, at 0 is 0.5. And this is the formula for the logistic function. So that's what I learned for the logistic functions. So the one aspect of this function is that as it moves away from the center, so that means if you are too big or if you are too small, then it's very slow. But if you are around the 0 and it goes up very quickly and it goes down very fast. And then we can think about this generalization of this function. So f of x is here. It is the original form. But suppose if you have two variables, say x and y, then you can write the form into two different ways. And the first thing we note that is that if you plug 0 inside the x, then this whole function becomes a simple logistic function. So you plug in 0 here, and then e to the minus 0 is 1. So this form is actually same as this one. And then the second thing note that is that if you add these two functions, it is always 1. And you can see the formula again. So g sub x and g sub y, it's not differentiation function. It's just a name for this function. So if you plug in 0, you will get the same form. And if you add two functions, you will get 1 always. And then the third property is that if you add the same amount of money, it is still the original form. That is the three property of the softmax function. So this is the softmax function, and I showed you the example of the two variables, but actually it can be generalized into k variable cases. And then if you add all these functions, you will always get 1. So it behaves like a probability. So that's why this function at the end, so some explanation.
To create these properties, you end the number classes for each of the output classes of.
So if you have 10 numbers, and that 10 number is actually not a probability, but there is a way to transform this 10 number behaves like a probability, and that's the softmax function. And the simplest example is that if you have only one number, then you can always transform that one number into a probability. And then if you have two numbers, then you can transform it into a probability so that when you add these two numbers, you will get 1. So that's the transformation of the softmax function, and that's it. So I think, yeah, this graph is a good place to start. We can also classify a neural network problem. Okay, of course, in general machine learning problems, there is a supervised learning and unsupervised learning. And in supervised learning, the problem can be classified into two categories. One is the regression, and the other one is the classification. The example of the regression problem is that the one we saw before, transforming the Celsius data into the Fahrenheit data. So how can you know which one is the regression and which one is the classification? Is that what is the output of the model? So if the output of the model is just a number, then that is a regression problem. And the output is as you can see here, is a listable number that represent the probability of something, then that is the classification problem.